Tutorial number 12, question number 1. Calculate the natural frequency of the vibration as mass is deflected from its equivalent position and released from rest. First, we need to define our coordination. We call this y. Then we have L, which is the length of the cable as well as the springs. We have L is equal to 3y, and dl is equal to 3 dy. This is equal to 3x. Then we have 3x is equal to x1 plus x2. Then x1 is the stretch in the spring k1, and x2 is equal to that of k2. Then we can draw the free body diagram of the pulleys. So this is by. Here's k1 x1. Here's t. And the upper pulley, here's T. Here's T, and this is K2 X2. Here's AY. Then we have T is equal to K1 X1, which is also equal to K2 X2. Then X2 is equal to K1 over K2 x1. Here's our equation number 2. Here's our equation number 1. Then we have from 1 and 2, we have x1 is equal to 3x over 1 plus k1 over k2. If we take a free body diagram of the mass, it will have K2 X2 T, K1 X1, K1 X1 T, and K2 X2. Then the Newton's second law, Fx is equal to mx double dot. We have negative 2 t plus k1 x1 plus k2 x2. This is equal to mx double dot. Then mx double dot plus 6k1 x1 is equal to mx double dot plus 18 k1x over 1 plus k1 over k2. This is equal to 0. Then we have its motion of equation. Then x double dot plus 18 k1 k2 m k1 plus k2 times x is equal to 0. Then omega natural is equal to 18 k1 k2 over n k1 plus k2 square root. This is equal to 10.39 radian per second. Then the natural frequency is equal to omega n over 2 pi. This is equal to 10.39 over 2 pi, which is 1.65 Hertz. Question number 2. Determine the damping ratio of the system depicted in the figure. The mass and friction of the pulleys are neglectable, and the cables remains taut at all the time. First, from constraint, we could say V2 is equal to 2V1 and A2 is equal to 2A1. We can do a free body diagram of the two masses. For mass 1, we have 2 tension from the cable and also the force from the damper, which is C x1 dot. Oh, by the way, we define this is our x1 direction. And for M2, we have the tension from the cable and as well as the force from the spring, which is Kx2, and this direction is our x2. And x1 is equal to 1 over 2 x2 because of the pulley right here. Then we can apply Newton's second law to these two masses. Then for mass 2, we have Fx, sum of Fx is equal to mx double dot. Then we have negative t minus kx2 is equal to m2 x2 double dot. For mass 1, we have 2t minus 1 over 2 cx2 dot, which is equal to m1 x1 double dot. This is also equal to 1 over 2 m1 x2 double dot. So from these two equations, we can eliminate tension. We can get m1 plus 4 m2 times x2 double dot plus cx2 dot plus 4kx2. This is equal to 0. Then omega n is equal to 4k over m1 plus 4 m2 square root. This is equal to 2 square root k m1 plus 4 m2. Then we have 2 zeta omega n is equal to c m1 plus 4 m2. Then zeta is equal to c over 2 times m1 plus 4 m2 times 1 over 2 square root m1 plus 4 m2 divided by k. So the damping ratio is equal to c over 4 square root k m1 plus 4 m2. Question number 3. The system is shown. Link AOB has mass m3 and ratios of gyration ko about 0.0. Ignore friction and derive the differential equation of the motion for the system shown in terms of variable x1. First, we could write the free body diagram for all the three masses. For m1, if we say this is our x1 direction, then m1 have k1x1 and also fa from the bar. For m3, it has the force from the bar, which is Fa also, and also we define this direction to Xa. And also it has the force from the damper, we call it C1Xa dot. And for point B, we have the force from the damper, we call it C2xB dot. And also it has force FB. For M2, it has FB and the force from the spring, it is K2x2. And we define this is our x2. By the way, here we call it theta. So we have a lot of coordinations, so we have to write several constraints. So we have xa is equal to x1 and xb is equal to x2. So xa over a is equal to xb over b. So xb is equal to b over a times xa. Also x2 is equal to b over a times x1. Then x2 dot is equal to b over a times x1 dot. Then x2 double dot is equal to b over a times x1 double dot. then x1 double dot is equal to AC that double dot. So if we apply Newton's second law to x1 direction, then we have fx1 is equal to m1 x1 double dot. For m1, we have negative fa minus k1 x1 double dot is equal to m1 x1 double dot. Then we have m1 x1 double dot plus k1 x1 plus fa is equal to 0. So for m2, we have fb minus k2 x2 is equal to m2 x2 double dot. m2 x2 double dot plus k2 x2 minus fb is equal to 0. MO, if we consider the momentum around the point O, we have MO, sum of MO is equal to IO theta double dot. Then we have FA minus C1 x1 dot times A minus FB plus C2 x2 dot times B is equal to M3KO square theta double dot. We have three equations. So we can solve our equation of motion, which is x1 double dot plus a square c1 plus b square c2 over a square m1 plus b square m2 plus ko square m3 x1 dot plus a square k1 plus b square k2 over a square m1 plus b square m2 plus ko square times m3 times x1 is equal to 0.